Hi, I've been trying to figure out how to show that video within this video and then talk about the central limit theorem, but I think I can't figure out how to make it work. So I really recommend watching this video that I have here first. It pretty much describes the central limit theorem a lot nicer than I think I can. And I think you'll get the picture, and then it will be easy, I think, to do the problems that we're going to look at on Monday. But let me just summarize what the central limit theorem says. So what it says, if you take a bunch of random variables, x1, x2, up to xn, and they could be anything. Maybe it's let's go with the time again that we spend in class. So if I just look at the distribution of every day, the time I spend in class, maybe it has an exponential distribution like this, where we'll say right around here, let's say the mean time is 45 minutes. So this distribution could go off long. Maybe sometimes I stay for 2 hours or something like that. But most of my times are probably under 45 minutes. That's where the bulk of the area is. This is the graph of x, the individual times. But if I started taking a random sample of times, so let's say x1, x2, x3, so let's say on 25 random days, I take times the length of my class, and then what I do is I average them and get this little x bar. The average is going to be very close. These little x bars are going to be close to 45, and if I graph little x bar for a bunch of sets of 25 data points, when I average them, I'm going to start getting a graph that's normally distributed with the center at 45. So this is pretty much what the central limit theorem is saying. If you take n random variables, and they don't even, the nice thing, they don't even have to be normal. So take n of them, non-normal, and then if I want to look at the distribution of capital X bar, which is the graph of all the little x bars, it's going to have a normal shape. And the mean is going to stay at the mean of the original distribution, mu. So my original x1 through xn had mean of mu and a standard deviation of sigma. So my graph of x bar, so the tight normal curve here is x bar, the center will still be at mu, which was 45, and the standard deviation over here, it's the original standard deviation sigma, but it's squished up by the square root of n, so it gets tighter. So for example, instead of taking 25 classes, let's say I take throughout the year 100 random classes that I teach, and I get x bar, and now I've plotted this x bar for 100. It's even going to be tighter than the graph I already have here, and the mean will stay at 45, but then sigma will be cut down by the square root of 100. So that's what the central limit theorem says. It pretty much guarantees us that that graph of x bar, which is the graph of little x bars, will have a normal shape. The mean will stay at the mean, and the standard deviation will squish up. And this next little box just says, if you start with normal, so if these x1 through xn are already normally distributed, then definitely x bar will be exactly normally distributed. The mean will stay at mu, and then the standard deviation will squish up again. So in the next few examples on this page, all I'm doing is I'm starting you off with a die throw, and the probability that you would get a 1, 2, 3, 4, 5, 6 if you rolled a fair die is 1/6. Now this distribution is pretty flat across the top. I mean, the probability of 1 and 2, all the way down to 6 is pretty equal. Well, it's equally likely, so these will eventually, if we do it enough times, will be pretty even across the top. So I took a random sample of 500 from that distribution, and I just put them in a bar chart, and you can see it's fairly even across. If I took a larger n, it would be more even. But now what I'm going to do is I'm going to take 2 die rolls and add them together. So imagine the mean of die rolls is actually a 3.5. So if you took something, if you add 2 die rolls, probably you're going to get something from the left side and something from the right side. If you just do a random sample, it's more likely you get one left and one right. So if you take those values, let's just say you got a 2 and you got a 6. If you average those, X bar is 4, right? Take 2 more. Let's say we get a 1 and a 5. We average those and we get 3. So we're going to start noticing a stacking up around the center. This is the most likely to occur is 3.5. I mean, to get all the way over here at 6, you would need your random sample to be a 6 from the first throw and a 6 from the second throw. And like the same way over here at 1, you would need 2 1s. So this has the least probability, but I'm starting to build up in the center near the average. So down here, what I went ahead and did is average those two. I took 2 die rolls and averaged them in Minitab, and you can start to see the shape. Actually, the sum of 2 uniforms is triangular. If I did it, now I'm going to add 3. So in other words, I'm going to do 3 die rolls. So let's say we got maybe the first die roll is a 2, the second die roll is a, I don't know, 5, and the third die roll is a 3. So now I'm going to take these 3 values. So this is 8, 9, 10. 10 divided by 3. Isn't this like 3 1/3? I hope so. And notice again, I'm getting near the center here. So when I add 3 die rolls together, I'm going to, and average them, I'm going to get close to 3.5, and I start taking on this normal shape where the tails are getting less likely. So for example, to get a 6, I'd have to get 3 6s and 3 1s, which isn't impossible. But if you think about Yahtzee, when we start averaging 6, it's very unlikely to be in the tails. So I did this for multiple n's. So there's n equals 3, n equals 4, a little bit tighter, and now you're seeing 1 and 6 less likely, and we're pulling in toward the center, the distribution is. So here is x, there's 5 of them for n equals 5. Sorry, I just lost that. Here is n equals 9, notice much tighter. And eventually I went ahead and did up to 25. The reason I'm using like 9, 16, 25 because square root of those values are nice, and I thought we might as well use things where the square roots existed as nice integers. So in each of these, what's happening is I'm taking the original distribution standard deviation and I'm dividing by the square root of n. So square root of 4 is 2, that's where I'm getting this 12 here. This would be 3 times 6, that's where I'm getting 18. So I'm squishing up every time my standard deviation. So let me go ahead and I did a couple problems. So this is an X bar problem. The X's come from, there are 100 of them, come from, well, I don't actually know. All I know is they come from some distribution whose mean is 1 and standard deviation is 0.5. So when I averaged them, the new mean should still be at the old mean, and the standard deviation then should be the old standard deviation divided by square root of n. And then I just go through with finding a normal probability. Probably you would do this in Minitab. Let's go down to maybe this one. Yeah, we might as well end with this one. So these 3 people went bowling together, and each of them, let's assume going into the bowling game, we know that each of their bowling scores are normally distributed with a mean of 120 and a standard deviation of 10. Now, because we started out normal, then X bar is going to be normal. That's why I'm not worried about X bar having a normal shape. If there were only 3 and they started off with a distribution that wasn't normal, let's say their bowling scores, even with a mean of 120, I mean, they could look, you know, they could look like this. But since I already started out with them being normal, then I know X bar will be normal. So the average of their 3 scores, that's x bar, the mean should stay at the mean, and the standard deviation should be squished up by the square root of n. And here then I'm just finding the probability using, I'm standardizing to get a z-score, but I could have done this in many tabs. So all you would have had to do is go to write the graph, probability distribution plot, put in the mean is 120, and the standard deviation is 5.77, right? So mu is 120, and sigma is 5.77. And we wanted to know the probability that their average for that game is less than 110, and 110 is, I'm not drawing perfect here, so we're just looking for this area right there. And we could have done that in many tabs. So I did it by a z-score, but I'm assuming probably you're going to use mini-tab for most of these. So let me know if you have any questions about this. I can do more examples, but tomorrow in class, that's what we're just going to spend our time on, doing X bar examples. Little over 10 minutes, sorry.